Good afternoon, ladies and gentlemen. My name is Jargalsaikhan. I'm going to talk about my research in experimental and numerical study of bioinspired alumina-based dental crown composites. Caries is the major cause of dental hard tissue damage and teeth loss. Here we can see from healthy teeth to an initial lesion and extensively damaged teeth image. It is an infectious chronic disease that has affected millions of people in the world. According to World Health Organization data, 3.2 billion people affected by oral disease in 2019 only. In England, 22 million adults were seen by an NHS dentist in 2018, and 9.7 million courses of treatments were held in the quarter-year period. There is many different varieties of treatments are available, such as direct restoration, crown, bridge, manufactured by different materials, such as metal ceramic and all ceramic materials, including zirconia. However, 20% of the ceramic used in top layers fail within 5 years of period. What can we do? Can we learn from nature and implement it into dentistry? Nature designs a perfect complex structure of living organisms from macro to the nano level. Nature has a simpler microstructure of aragonite platelets held together by proteins that provides good fracture resistance. Here we can see macro to nano structure of nacre. This layered structure induces several toughening mechanisms, such as crack dissection and platelet sliding. And is this possible to manufacture this structure? Yes, using bidirectional freeze casting technique. This technique is cost-effective, but also allows us to achieve layered ceramic scaffold. According to the literature, alumina-based composites exhibited promising results on fracture toughness while preserving its strength. Here we can see manufacturing process of bioinspired ceramic-based composites from scaffold followed by wax infiltration, uniaxial pressing, and sintering. And finally, we could achieve alumina-based PMMA composites by infiltrating polymer. We have used the Deben Macrotest 5000 integrated within scanning electron microscopy. And here I would like to show synchronized in situ ACM and Deben recording, where we could achieve recorded crack propagation and load and unloading of elastic compliance testing. In this window, we can see load and unloading, while here we can also track crack growth. For data analysis, we are following ASTM E1820 standard, which we have calculated J value from each cyclic loading point by decomposing it into the elastic and plastic contributions. Here I would like to talk about the elastic compliance test of alumina-based PMMA composites. These ACM images were taken at the start of the test, which we can observe microstructure of the composite. And also crack extensions were recorded. Here is the ACM image, an extension of 0.1 millimeter. And the crack failure image which we were taken at the end of the test. The staple crack growth with longer extension since crack initiated, which implies plastic behavior of composite sample. The bioinspired composites displayed R-group behavior and the fracture toughness higher than monolithic aluminum. Both ceramic layer and polymer phases are contributing to the toughening mechanisms. In the case of ceramic layer, if the layer breaks, crack grows without deflection. But when bridge breaks, crack grows with deflection. When the transferred stress is lower than bulk strength, fracture requires pull out of the ceramic, which dissipate more energy. In the case of transferred stress higher than bulk strength, fracture occurs within the ceramic phase, resulting catastrophic failure. Polymer phase plays a role in arresting the cracks through the mechanisms of crack tip blunting and bifurcation. A thick polymer layer can bear a load by offering extensive plastic deformation. It can contribute to the fracture toughness of composites. But when polymer phase is thin, it can also act as lubricant, which relieves stress in the composite by offering frictional sliding between ceramic layers, thereby increasing the crack resistance. All these properties are influencing the intrinsic toughening mechanisms of composite material. In conclusion, the bioinspired composites displayed R-curve behavior and the fracture toughness higher than monolithic alumina. The PMMA composites have a higher toughness. The increase in toughness was the result of multiple toughening mechanisms, including crack deflection, crack bridging, branching, and microcracking. This work is important for the development of new generation dental crown composites, as it provides insight into potential strong and tough material combinations. However, future optimization in composite composition for optimal material properties is required. In-depth fracture toughness comparison and monotonic and cyclic in situ micromechanical testing results are ongoing. Also, 2D FEM fracture modeling work is ongoing for validation and optimization. And thank you for your attention.